In today's video we're going to look at solving different types of trigonometric equations. We'll start off with some simple ones and then look at changing the angle that's inside the trigonometric function, and then we will look at some more difficult and challenging equations that you may need to solve. So the first set of examples that I'm going to look at, I'm going to look at solving 2 sine x is equal to negative the square root of 3, and a lot of the time they will give you an interval in which you need to solve this particular equation. If they don't, then you're going to have to solve it for all real numbers, and we'll come to that in a bit. But first of all, I'm trying to find any angle such that 2 sine x is equal to negative the square root of 3. Well, that tells me, by simplifying this and just getting the trigonometric function on one side and all other values on the other side, that sine of x should equal negative the square root of 3 over 2. I'm looking for any angles such that the sine of that angle is negative the square root of 3 over 2. Well, if you refer to the unit circle, you'll see that the angles for which that happens are 120 degrees and 240 degrees. So that tells me that for these angles, sine of those angles is going to have the value negative the square root of 3 over 2. So the y-coordinate of where the terminal side of that angle hits the unit circle, that y-coordinate is going to be negative the square root of 3 over 2 for these two angles. Next, let's look at a cosine problem where we have 5 cosine x minus 5 equals 0, and again I'm going to look for x within the interval 0 to 360 degrees. I'm going to do the same thing again. I'm going to simplify this by getting the trigonometric function on one side and all other values on the other. So I am looking at what angles give me an x-coordinate on the unit circle of 1. Well, there is only one angle where I have an x-coordinate of 1, and that is that x is equal to 0. Okay. I also want to point out for this particular example, we are not including 360 degrees. 360 degrees is coterminal to 0, and therefore we do not include it in this interval here, so the only solution within that interval would be x is equal to 0. Next, I'm going to look at some different problems using radians, but I'm also not going to specify an interval here. We're going to do this for all real numbers. So I'm going to find all real number solutions and this time in radians to 2 sine x is equal to negative the square root of 2. Okay. I'm going to do the same thing again. I'm going to simplify it and bring the trigonometric function on one side, all other values on the other. Once you get to this point, if they have not specified an interval, what I want you to do is to find all angles for which this is true on that first wrap of the unit circle. So first we're going to look for all angles in radians between 0 and 2 pi for which this is true. So what angles have that y-coordinate for the terminal side on the unit circle of negative the square root of 2 over 2? Well, it turns out that if you look on the unit circle, those values are going to be 5 pi over 4 and 7 pi over 4. They have a y-coordinate of negative the square root of 2 over 2. But all angles coterminal to those angles also have a sine value of the negative the square root of 2 over 2. So what I'm going to do here, there's different ways that you can write this. is I've written plus 2k pi at the end of each one of these, where k is any integer, positive or negative. That gives me every integer multiple of 2 pi that I'm adding or subtracting, because k can be negative, from the original value. That gives me all angles that are coterminal to those angles that satisfy my equation within the first wrap of that unit circle. So I'm just adding all integer multiples of 2 pi to this, and therefore that is all real numbers in radians that satisfy this equation. So whenever you get one of these, always simplify it as much as you can. Then we're going to look at the first wrap of the unit circle, see which angles actually do satisfy that equation in the first wrap of the unit circle, and then we add on every multiple of 2 pi to that, and that will include all angles that are coterminal to those angles that are in that first wrap of the unit circle. And we will specify here that k is an integer. Next example is we are going to find all real number solutions again in radians to this time 6 cosine x plus 3 equals 0. I'm going to do the same thing again. Keep my trigonometric function on one side, all other values on the other. So when you do that, you're going to subtract 3 and then divide by 6, which gives me cosine of x is equal to negative 1/2. So which angles in radians in my first wrap of my unit circle have an x coordinate, a cosine value of negative 1/2? Well, it turns out that those values are 2 pi over 3 and 4 pi over 3. Okay, they're in quadrant 2 and 3 respectively. And again, every angle that is coterminal to those angles also satisfies that cosine of that angle is negative 1/2. So we add every integer multiple of 2 pi to each of those angles, and that gives me all real number solutions in radians to my equation. Finally, for this section, I'm going to look at find all real number solutions again in radians. To tan x is equal to the square root of 3. Okay. What I would do here is I would remember that tan of x is sine x over cosine x, and the way that I would get the square root of 3 is either when sine x is equal to the square root of 3 over 2 and cosine x is 1/2, or when they are both negative. So either I've got the positive or negative of the square root of 3 over 2, but then the same sign, positive or negative, of 1/2 for cosine. Okay, so we are looking at angles that are going to be in quadrant 1, where both sine and cosine are positive, so I get sine of the angle is square root of 3 over 2, cosine of the angle is 1/2, or I'm in quadrant 3, where sine of the angle is negative the square root of 3 over 2 and cosine of the angle is negative 1/2. Both of those situations give me tan of the angle is the square root of 3. And the values for which that is true would be pi over 3 and 4 pi over 3. And again, any angle that is coterminal to those angles also satisfies my equation. What happens if the trig equation involves multiples of an angle inside my trig function? So, for example, let's look at solving. I'm trying to find all real number solutions, again in radians, to this equation. This is going to work very much the same way as before. You just have to do an extra step at the end. So again, I'm going to bring my trig function on one side, all other values on the other. So that gives me sine 3x would equal negative 2 the square root of 2 over 4. You can cancel that down, which would be negative the square root of 2 over 2. I'm just going to look for any angle that gives me sine of that angle is negative the square root of 2 over 2. That would be 5 pi over 4 and 7 pi over 4. Okay, so we're in quadrant 3 and quadrant 4. So that tells me that 3x is equal to 5 pi over 4, and again, any angle that's coterminal to it, or 7 pi over 4 plus or minus 2 pi and any multiple of 2 pi. So I'm looking at all angles that are coterminal to those two angles that are in that first wrap of that unit circle. But that is true for the angle 3x. Okay, so sine of that angle, sine of these angles, equals negative the square root of 2 over 2. I've got to find x, which means I need to divide these solutions by 3 at the end. So you're going to solve it very much the same way as you would like our previous problems, but at the end you have to worry about simplifying it so that you just get what x is, not 3x. Okay, so we're going to divide everything through by 3. So we will get 5 pi over 12 plus 2 pi over 3 times k. That's how I'm going to write this. So it's multiples of 2 pi over 3 that we're adding or subtracting from 5 pi over 12. And then 7 pi over 12 plus or minus any multiple of 2 pi over 3. So you have to divide everything through by 3 at the end. So solve it very much the same way as we did at the start, but at the end you have to divide through by whatever number is in front of the x. One more of these that we will do. We're going to look at solving 3 tan 1 over 5x plus 3 the square root of 3 equals 0. Keep your trig function on one side, all other values on the other, so that would give me tan of 1 over 5x is equal to negative the square root of 3. What angles give me tan of the angle equals negative the square root of 3? Well, it's almost the opposite of what we had in this situation here. You would be looking for angles where sine of the angle was positive the square root of 3 over 2 and cosine of the angle was negative 1/2, so you're looking for opposite signs between sine and cosine here. Well, sine of the angle is negative the square root of 3 over 2 and cosine of the angle would be 1/2. That would give you negative the square root of 3 for your tan value. So this time we would be looking in quadrants 2 and 4, and that would tell you that the possibilities for 1 over 5x would be 2 pi over 3 plus any integer multiples of 2 pi, or 5 pi over 3. So now to find my solution, I just multiply everything through by 5. So that would give me that my set x is equal to 10 pi over 3 plus 10k pi, and then 25 pi over 3 plus 10k pi. Now I'm going to look at the examples where we will have an angle that's added or subtracted to that value x inside that trigonometric function. So for this example, I'm going to look at solving cosine x minus pi over 5 is equal to negative 1/2. So exactly the same as what I have done before. I'm looking for the angles such that cosine of that angle equals negative 1/2. Then I will deal with that pi over 5. So the first wrap of the unit circle, we get cosine of the angle equals negative 1/2 when the angle is 2 pi over 3 and 4 pi over 3. So this happens in quadrant 2 and quadrant 3. And then every angle that is coterminal to those angles also gives us cosine of the angle equals negative 1/2. So that tells me that the angle x minus pi over 5 must equal one of these two. Now I've got to add pi over 5 to both of these in order to find my solution. So x is equal to 2 pi over 3 plus pi over 5 plus any angle that is coterminal to that. So 2 pi over 3 plus pi over 5 gives me 13 pi over 15 plus integer multiples of pi, and then 4 pi over 3 plus pi over 5 gives me 23 pi over 15 plus integer multiples of 2 pi. So for any of these examples where we are adding or subtracting an angle from the x value inside the trigonometric function, it works exactly the same way as the previous examples. It's just that at the end you are going to have to add or subtract an angle from each of the values inside the set. Now I want to look at some trig functions where we're going to have to use some factoring. So we're going to be solving these by factoring. The first example I want to look at is 4 sine squared x is equal to 2. Okay, and I want to solve this again in radians, and I'm looking for all real values for which this is the case. Same as before, I'm going to get my trig function on one side, all other values on the other side. So that gives me sine x is equal to 2 over 4, which is 1/2. And then I take the square root. So sine x is going to be plus or minus the square root of 1/2. And the square root of 1/2 is the square root of 1 over the square root of 2, which is 1 over the square root of 2, which, when you rationalise the denominator, is just the square root of 2 over 2. So I'm looking for all angles for which the sine of that angle is either positive or negative the square root of 2 over 2. If I look at the first wrap of the unit circle, I get pi over 4, then I get 3 pi over 4, 5 pi over 4, and 7 pi over 4. All of those values give me sine of that angle equals positive or negative the square root of 2 over 2. And then obviously any angle coterminal to these is also going to give me positive or negative the square root of 2 over 2 when I take sine of the angle. This is a lot of different angles, and we can actually simplify this set fairly easily. What I'm going to do in order to do this is to look at which sets I can actually combine. If we look at this set here, pi over 4 plus integer multiples of 2 pi. If I take pi over 4 and I add pi to it, I end up at 5 pi over 4. When I'm at 5 pi over 4, if I add pi to that, I'm going to end up at 9 pi over 4, which is just pi over 4 plus 2 pi. So I'm back in this first set again. Then if I add pi to that, I'm going to end up back in this set. So each time I add or subtract pi, I just go between those two sets. So I can combine those as pi over 4 plus integer multiples of pi. Okay, I just add and subtract multiples of pi to pi over 4, and I can combine both of those together. Same thing happens with the other two. If I take 3 pi over 4 and I add pi to it, I end up at 7 pi over 4. If I add pi to it again, I'm at 11 pi over 4, which is in this set. If I add pi to it again, I'm in this set. Same happens when you subtract pi, you just go between the two sets. So I can combine those as 3 pi over 4 plus integer multiples of pi. So this just simplifies to x is equal to pi over 4 plus integer multiples of pi and 3 pi over 4 plus integer multiples of pi. The next example is going to involve a lot more factoring. So for this one, we're going to look at sine of x times cosine x minus sine x equals 0. And I want to solve this. Okay. First thing I'm going to do is factor this. So I can see that sine of x is in both terms, so I can pull that out. So I get sine of x multiplied by cosine of x minus 1 equals 0. Same as when you factor any polynomial. This tells me that either sine of x is 0 or cosine of x minus 1 equals 0, or both. So that gives me that sine of x is equal to 0 or cosine of x minus 1 equals 0, which means cosine of x equals 1. So I need to find the angles x such that one or both of these is true. Okay. Where is sine of an angle 0? Well, I know that at the angle 0, sine of x equals 0. Okay. The y-coordinate when the angle is 0 is 0. Okay. It just so happens that at the angle 0, cosine of 0 equals 1. So at 0, both of these things are actually true. And the same goes for any angle that is coterminal to 0. So I know already that a set of angles for which actually both of these things is true is 0 plus any integer multiple of 2 pi. So all the angles that are coterminal to 0. Okay. Sine of x also equals 0 at pi. Okay, sine of pi equals 0. The y-coordinate at pi equals 0. And the same goes for any angle that is coterminal to that. So I also have to add in pi plus any angle that's coterminal to it. So we're adding and subtracting multiples of 2 pi. Okay. There is no other angle for which cosine of x equals 1 that isn't included already here. So that is the set of all angles for which one or both of those things is true. I can again combine those exactly as I did the last time. Okay. I start at 0. Okay. If I add pi, I'm in this set. If I add another pi, I'm in this set. Add another pi, I'm in this set. So each time I add or subtract pi, I just flip between the two sets, which tells me that I can combine these as 0 plus integer multiples of pi. Well, 0 plus integer multiples of pi is simply just integer multiples of pi. So that is my solution here. The final example that I want to look at is slightly more difficult, and if you ever got a problem like this, I would help guide you through it. It's not exactly the easiest thing to see what you would do here, so I would give you some guidance. And the question is, we want to solve and find all solutions to cosine of x is equal to sine x. And I want to find all angles for which this is true. Okay. The way that we are actually going to do this, and the way that we start, is by squaring both sides, and this will make sense in a minute. If I square both sides, then I'm going to do exactly what I've done in previous problems and get all of my trigonometric functions on one side, any other values on the other side. Okay. Why have I done this? Well, it turns out that this is actually familiar to us. That is actually the double angle formula for cosine. So cosine squared x minus sine squared x is equal to cosine 2x. So I am actually looking for all angles x such that cosine 2x equals 0. So first, let's look at any angles for which cosine of the angle equals 0. Well, in my first wrap of the unit circle, that happens at pi over 2 and 3 pi over 2. So obviously it also happens for any angles that are coterminal to those. Okay. Then I have to divide through by 2 because it's cosine of 2x equals 0. So my angle is 2x, so I'm now going to divide through by 2, which gives me pi over 4 plus multiples of pi and 3 pi over 4 plus multiples of pi. Okay. That's two different sets. We've got pi over 4 plus multiples of pi and 3 pi over 4 plus multiples of pi. The issue here is, and this is something that, again, I would guide you through, we need to check these solutions. The reason being, when we squared this at the top, we're negating any sign differences, okay? If something was positive and you square it, it remains positive. If something was negative and you square it, it then becomes positive. So we actually need to make sure that squaring this hasn't done any damage in terms of sign differences. So I'm actually going to plug both of these sets into sine and cosine to make sure that they are the same. So first, cosine of pi over 4 plus multiples of pi. Okay. That means that I'm looking at cosine of pi over 4, or any coterminal angle to pi over 4. We're in quadrant 1. Pi over 4 plus pi puts me at 5 pi over 4, and I'm now down in quadrant 3. So I'm also looking at all the angles that are coterminal to 5 pi over 4. When we're in quadrant 1, cosine of the angle is positive the square root of 2 over 2. When we're in quadrant 3, cosine of the angle is negative the square root of 2 over 2. Cosine of 5 pi over 4 is negative the square root of 2 over 2. And it goes the same for each of those angles that's coterminal. So whenever we've got the angle in quadrant 1, cosine of that angle is positive the square root of 2 over 2. When we're in quadrant 3, it's negative. Now let's look at sine of angles in this set. Okay. Again, sine of any of the angles that are coterminal to pi over 4, so pi over 4 plus multiples of 2 pi, that's always positive the square root of 2 over 2. But pi over 4 plus pi, that puts me at 5 pi over 4, I'm in quadrant 3. Sine of any angle in quadrant 3 is negative. Sine of 5 pi over 4 is negative the square root of 2 over 2. So again, same as with cosine. When we're in quadrant 1, any angles in these sets that are in quadrant 1, sine and cosine are both positive the square root of 2 over 2. When they're in quadrant 3, sine and cosine of those angles are negative the square root of 2 over 2. Now let's look at my other set. Okay. 3 pi over 4 is in quadrant 2. Cosine of 3 pi over 4, again, cosine of an angle in quadrant 2 is negative the square root of 2 over 2. If I add pi to that, I'm now in quadrant 4, and I'm at 7 pi over 4. Cosine of 7 pi over 4 is positive the square root of 2 over 2, and same goes for any angle that's coterminal to that. So cosine of any angle in this set that's in quadrant 2 is negative. Cosine of any angle in this set that's in quadrant 4 is positive. Now for sine of angles in this set, okay, sine of 3 pi over 4 is positive the square root of 2 over 2. Sine of 7 pi over 4, or any angle that's in quadrant 4, is negative. These have opposite signs. Okay, so for each of these angles in the same set, sine and cosine, although they have the same absolute value, they are actually different values. Some are positive, some are negative. Okay, so cosine of 3 pi over 4 is negative the square root of 2 over 2. Sine of 3 pi over 4 is positive the square root of 2 over 2. They're not equal, meaning that this thing does not hold true. Okay, so my solution is actually just any x, which is pi over 4 plus multiples of pi. This is not in the solution set. So it's always, at the end, I would always say to you in a problem like this, go ahead and check your solution. Okay, and this is why, because sometimes if you would have squared it or something at the top, that squaring will have done something to the signs, and therefore that is why we had this issue.